Alright, you guys, welcome. We're talking about parallel lines and triangles today. And parallel lines actually help out with triangles quite a bit. Okay, first off, we do need to define some stuff. Okay, so let's say I draw a line. Pretty simple. Okay, and let's say I pick a point off of that line. Okay, now through that point, there's only one line that exists that is parallel to this first line that I've drawn. Okay, and what that does is that helps us from this theorem actually, and you're thinking like, yeah, that makes common sense. But some people would try to argue, oh, you could draw a line like this and have it go through here like this, and it's a separate line. It goes through the same point, and it is also parallel, when in fact you can clearly see it is not. Okay, so just as we work with that stuff, that's going to help us out. Now also, that also helps us draw an auxiliary line. Okay, so an auxiliary line is a line that we draw to do proofs, and one of the more famous proofs is, since we're moving into it, we're going to start talking about some triangles. Okay. Now, if we actually take a look at the actual triangle, looks something like this. There we go. Okay, and we have, let's call this angle A, angle B, and angle C, and obviously you guys know you can draw it by a couple other names. Okay, and you would actually need to use an auxiliary line. Okay, let's go boom, boom, boom. Let's make it green. Okay, you would use an auxiliary line to be able to prove it. But long story short is, okay, here's a trick you can do to prove the angles inside of a triangle. The interior angles add up to 180. Okay, make a triangle, then tear off the three edges. Okay, so if we cut, now this is not a paragraph proof, or this is not a a formal type of proof, but if you tear off the sides, the angles, and you line them up, okay, so in other words, I put angle B right here and angle C right here. Nope, actually it's reverse. Sorry, I always if you put angle B right here and you put angle C right here, you would actually have them line up to make a straight line. So therefore, you could say, oh, the entire thing is 180 degrees. So that's kind of the cool thing about this that really just helps out, is your auxiliary line actually helps out explain why the sum of the interior angles is going to be 180 degrees. Okay, now we do need to talk a little bit about some stuff, especially talking about with a certain kind of theorem, and I'm going to explain it in a sec. So let me see. Okay, so we have the theorem for a triangle, and we're getting into triangles, so we're going away from regular lines. I mean, we've already talked out the butt about lines, so now we're going to talk about triangles. First one you need to know, I just talked about sum of interior angles in a triangle is 180 degrees. Let me see, what is that degree symbol? Alt 248. Okay, and yes, it is so important that I typed it in all caps. I accidentally typed in all caps, I left on the caps lock. Okay, so sum of interior angles inside of a triangle is 180 degrees. Now there's another one that's just as important, and this is kind of cool. Okay, let's say this was angle A, this is angle B, and this is angle C. Okay, so in other words, angle ABC plus angle BCA plus angle CAB is going to be equal to 180 degrees, so that's the formal definition. Okay, and I am using the less than sign just because it looks like the angle sign in there. Okay, but also here's another interesting thing. All right, this angle here plus this angle here will equal this angle out here, and that's called the exterior angle theorem. Okay, so in other words, angle 1 plus angle 2, and I'm using this triangle as reference, is equal to angle 3. Okay, and that's an amazing coincidence. It's just a really cool thing to know that these two angles inside of the triangle, and these are called remote interior. Okay, so that helps out with that definition, that these two are going to be equal. Okay, so it's really just kind of nice to know that those aren't. It's not an approximation, it is an exact answer. Okay, all right, now why does it work that way? Well, let's say we had angle 4. Let's say we had angle 4. Well, we know that angle 4 plus angle 3 is going to be 180 degrees because that's a linear pair. But, okay, angle 4 plus angle 2 plus angle 1 is going to also equal 180 degrees because they're inside of a triangle. Okay, so therefore, angle 4 plus angle 3 is 180. Angle 4 plus angle 1 and 2 have to be 180. So by the law of syllogism, ta-da, using proofs, angles 1 plus 2 has to be equal to angle 3. Just as simple as that. Okay. Plus also, these are a supplementary pair. So if I make these a pair of numbers, these pair of numbers, the sum, if I make that one number, that makes these a supplementary pair as well. So, well, that makes these a supplementary pair, and therefore these two are equal. So that's where the law of syllogism really comes into play. Now, does that work for all the angles? Yes, it does. So if I were to continue to draw off at certain angles, let me move this one over a little bit, and then we'll start drawing out theorems. Okay, so if I were to work it out, I would be able to get it. So let's say that this was angle 5 and that this was angle 6. Okay, so we could also say angle 1 plus angle 4 is equal to angle 5, and we could also say angle 2 plus angle 4 is equal to angle 6. Okay? And so you could say all of those, and that would be an exact true statement about a triangle. So that's the that's the really cool stuff about it. Now, this also helps with a certain proof. Okay? And some people they try to prove, like, you know, if a line really is parallel, why doesn't it touch down the road? Okay, and this is called a proof by it's called a proof by negation. I don't think it's exactly called that, but anyways. Okay, how do you know if two lines are perpendicular to a third line, a transversal? How do you know if these two are not going to be parallel? Okay, now if you remember when we were talking about proofs, you can basically bend a lot of arguments a certain way. So a famous argument that's taken, okay, is one of, what if my lines are parallel for a long time, but then all of a sudden down the road they cross, and I create a triangle? Okay, so now I've disproved that they're parallel, right? Well, if I cross, okay, it doesn't matter what this angle is. This could be like whatever. Okay? All right, these two angles, and this is the really cool thing about this proof. Come on. These two angles are remote interior angles from here. So therefore, these two angles need to add up to be equal to this angle out here. Well, if you're paying attention, this is 90 degrees. This is some angle. which is just, bigger than 1, angle bigger than 0, okay? And they need to add up to be bigger than this, or they need to be equal to this angle. Well, last time I checked, 90 plus something is not equal to 90, okay? So therefore, they never cross, and therefore, okay, therefore, they never cross, and therefore, they're always going to be parallel. Ta-da! Proved it. So that's a cool thing. And you can also work it for the reverse side, like, well, what if they're going out at an angle that's going to the left and going to the right? Well, now you have the other side and you can still use it. So what you can do is you can use the exterior angle theorem to actually prove why two lines that are perpendicular to the third transversal are never going to be not parallel. So that's kind of cool how it works that way. All right, I think I spent a lot more time than I needed to on this, but I just want to show you guys some cool stuff about it. Okay, remember, set up your algebra and use these formulas to help yourself out. Okay, thank you.